Greetings, welcome to our 49th episode of the FGI podcast series. My name is Tim Stark and I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign. On today's episode, we are going to focus on our July 13th, 2023 webinar titled Static and Seismic Deformation Analyses for Bottom Landfill Liner System Interfaces. I'd like to quickly reintroduce my co-presenter for this presentation, and that's Jala Lin. Jala recently completed his PhD at the University of Illinois at Urbana-Champaign and performed all the analyses that we presented, and all those analyses are part of his PhD dissertation. So first are the questions from the live webinar presentation that we did not get to, and there are approximately 20 of those. So thank you very much for all of your questions and interest in the study. And this podcast is going to try to answer all of them. If not, please send me or Jala a message and we will correspond with you directly. And let me get that out of the way right now. Jala's email is JalaL2, and that's JIALEL2@illinois.edu, or you can email me, tstark@illinois.edu, or Jen Miller at fabricatedgeomembrane@gmail.com. So here we go on the first question. Do you consider probable differential settlement deformations at the base of your model? The bedrock underneath the landfill is fairly stiff, so there was no settlement considered of the bedrock underlying the bottom liner system. And in fact, the compacted soil subgrade that supports the secondary geomembrane was extremely stiff. In fact, I could not penetrate it with a shovel to get a sample of it. We had to use a pick to break up the subgrade to sample it. So very, very stiff, and that's underlain by bedrock. Should you include leachate head in the stability models if you already have accounted for wetted surfaces in the direct shear testing of the interfaces? Or should you always include both in the analysis? You should include both. The pressure head should be included with the direct shear tests on wetted or soaked geosynthetic interfaces. Now, the wetted and dry specimens in the direct shear and ring shear yielded, no, I better just say direct shear. In direct shear, yielded similar interface strengths, and thus we did not differentiate between the wet and dry interface test in direct shear. But the peak strength in the ring shear device is lower, and so that could be modeled in the analysis because moisture had a bigger effect in the ring shear test. Question number 3, which interface was typically the most critical or the critical in your analysis? Was it the same interface for base and side slope? The interface, the critical interface, and there's only one critical interface in the analysis, and that is the same for the base and the side slope. And that critical interface is the secondary geomembrane and the overlying leak detection zone geocomposite. Okay, so the liner system consists of a primary geomembrane underlain by a GCL, underlain by the leak detection zone, which is a geosynthetic geocomposite, and that's underlain by the secondary geomembrane. All the sliding and movement on the base and slide slope occurred at the top of the secondary geomembrane. Question number 4. Previous studies such as Wu 2000 and Gao, Kavazanjian, Wu 22 showed displacements largest at the slope crest, dissipating to 0 at some point down the slope. Can you comment on why your study differs, i.e. little to no deformations at the top of the slope. That's because at the top of the slope, the geosynthetics were anchored in an anchor trench. So there is no displacement at the top. If the materials, the geosynthetics, were not anchored in an anchor trench at the top, you could have displacement at the top, but that was not the particular case that Jala modeled. Question number 5, how would a megathrust earthquake event like the Japanese earthquake of 2011 change these analyses? Wow, great question. So instead of fairly small shear displacements along the critical interface, that large earthquake in 2011 would have induced significant deformations, which would have taken the interface from certainly post-peak out to residual. And if the slope would be unstable at the residual strength, interface strength, the slope would have failed during or shortly after the earthquake. Question number 6. Is all of this analysis applicable to heap leach pads? Some additional considerations to be taken for application to heap leach pads. The model that Jala developed for the code FLAC to calculate the shear displacements along the bottom liner system is applicable to heap leach pads. Of course, you would use different material properties for the heap leach materials than you would for municipal solid waste. But the analysis would be the same, and in fact, you could use, if the texture geomembrane drainage composite was the critical interface, you could use the same direct shear results, extrapolate them out to residual, and use the model that Jala presented. Question number 7. Comment regarding leachate head. Regulations require maximum head on the bottom liner system to be less than 1 feet. This site has some issue about the leachate head. The head measured is a little lower than 1 foot, but this could be considered to be the worst case scenario. So what we were trying to do with the leachate head is predict what effect, or estimate what effect, if leachate did pond up in the bowl or bottom of the landfill, hypothetical landfill, what effect that would have on the calculated factor of safety. So this goes back to an earlier question. You would include a piezometric head or leachate head, because that affects the effective normal stress acting on the critical interface. And you would use the direct shear results that reflect a wetted condition. So the leachate condition would match the interface being wetted as well. Okay, number 8. Hi, Tim. Have you published a paper that summarizes the parametric studies that you presented and recommendations for when to use peak, post-peak, large displacement, and residual interface shear strength values? We have not published it. Jala is working on that paper, and if you send Jala a message, we will send you a draft of the paper as soon as it is ready. Okay, question number 9. On slide 47, it states never use peak strength on side slope. However, the table indicates otherwise for slopes flatter than 4:1. Please clarify. Okay, great question. So what we want to do is be careful on the side slope. So you're right. For a 4:1, 5:1, and 6:1 side slope, that's short. So this is the shortest side slope, 80 meters. You could use, or the analysis says you could use peak strength. All the other slopes, these 160 meter long and 240 meter long slope, it mobilized a strength less than the peak. So I think the best rule of thumb at this point, given uncertainties in modeling and so on, is never use a peak strength, interface strength, on a side slope. Okay, number 10. Are there any recommendations for preparing a power function to fit available direct shear interface friction test data that can help forecast a plausible residual strength at higher displacements. Many interface testing specifications are limited to direct shear testing. Absolutely, and that's unfortunate. That's why Jala performed torsional ring shear tests so we could actually understand and measure the true residual strength of the geosynthetic interface. Jala has prepared a paper on using a power function to fit available direct shear test results. It has been submitted for review to a journal publication. I think, Jala, you can share a draft of that paper. So if you're listening, please send Jala a message at jalall2@illinois.edu, and we'll send you a draft. It's currently under review, so don't distribute it, but you can see how Jala fitted a power function and the A and B coefficients that it used to fit the power function. Okay, question number 11. Can the cam clay model incorporate strain hardening, which is often observed in waste materials? Yes, the cam clay model can handle strain hardening, and you just have to input a strain hardening parameter into the model, and it will consider strain hardening. Number 12, can you provide a summary of the assumed geomembrane physical properties, particularly the asperity size or asperity height of the texturing of the secondary geomembrane? Okay, here are the properties. The peak friction angle of the secondary geomembrane drainage composite interface is 21.7 degrees, and the adhesion is 15 kPa. That's peak strength parameters. Large displacement strength parameters at 3 inches or 75 millimeters of displacement are friction angle 13.4 degrees and adhesion of 5.1 kPa. Lastly, the residual friction angle of the interface is 9.7, and there is 0 adhesion at the residual interface strength condition. The asperity height of the geomembrane specimens that Jala tested in ring shear range from 24 mil to 36 mil. And that also goes for the direct shear specimens as well. So asperity height 24 to 36. Question number 13, aren't you limited to 30 centimeters of head on the bottom liner system? Yes, that is the 1 foot of leachate head on the bottom liner system. So what we were doing with that analysis is studying the effect of a leachate head developing on the liner system that is higher than 30 centimeters or 1 foot, and what effect that had on the factor of safety, because as the leachate head increases, the effective stress on the critical interface decreases, and as that effective stress decreases, the interface strength decreases, which would decrease the factor of safety. Number 14, did the model use saturated soil mechanics to revise the material properties as leachate accumulated in the system? Jala just used the piezometric head or pressure head on the base of the landfill. Unsaturated soil mechanics can improve the model, but there wasn't much effect of changing the waste from unsaturated to saturated on the analysis. Okay, number 15. I would like to obtain a copy of the fish code, as I see it as a potential tool for when looking at a range of uses of geosynthetics in landfills, tailing storage facilities, etc. Absolutely, we agree, and you can obtain the fish code from jalall2@illinois.edu. So I'll spell it out: JIALEL2@illinois.edu. Jala's email is also on the slides, which you can download from the FGI website. Question number 16. Jala, how long did it take you to develop the base liner system model in flat? Jala, it took him 1 to 2 years as part of his PhD research. Number 17, if I understand the explanation of the stage placement, if biodegradation of the waste was considered in the model, then there would be additional shear loading on the liner system. Is this correct? Absolutely. And it's this biodegradation which induces additional displacement or settlement of the waste. And as the waste settles, it imposes shear stresses along the critical interface. And those shear stresses produce additional shear displacement, which reduces the mobilized interface strength, critical interface strength, from whatever value it's out at currently towards the residual. And that's why earlier I mentioned never use peak strength, interface strengths on the side slope, even though Jala's analysis for short side slopes indicates a peak strength may still be available. Okay, number 18. Was there any consideration given to applying rainfall onto the waste during placement and before the final cover system was placed that would lead to additional loading? That's a really good question. Rainfall was not added to the waste or additional infiltration to the waste, but that could have had some additional impact. It could have softened the waste a little more, inducing more settlement in the CAM clay model and thus more down drag or shear stresses in the bottom liner system, especially on the side slope. Okay. Number 19, last question of the questions from during the webinar. Based on the response to my question regarding the use of the modified CAM clay model, is it not possible to select, say, the original CAM clay model, which better represents soil behavior? For your information, I'm not a fan of the modified CAM clay model for use in professional practice. Yes, you can use the original CAM clay model instead of the modified CAM clay model, as long as the parameter fits the actual test results in the model. So remember, Jala verified the fish code and the input parameters by comparing the results with the actual measured direct shear results. So that's one way he validated the model, is he basically simulated a direct shear test and then matched the results to it. And Jala, please jump in there if I misspoke on number 19.
It's good. Basically, just need to fit the test result when they use it in the numerical simulation.
Okay, but what test result are they fitting?
Triaxial test usually for CAM clay models or modified CAM clay models.
Oh, right, triaxial test of the waste, on the waste. Right, so you can verify the original CAM clay model in the literature, and Jala can send you some references to triaxial compression tests performed on municipal solid waste, and you model the triaxial compression test in FLAC with the original CAM clay model and make sure the response matches what's measured in the triaxial compression test. Okay, now let's shift to the questions submitted after the live presentation, and there are 4 of these questions. Are there peer-reviewed papers, number 1, are there peer-reviewed papers available related to extrapolating large displacement shear strength to residual? Yes, Jala's working on that paper. He has it. We've submitted it for review and possible publication. He can send you a draft of that paper, so just send him an email message. How was the seismic ground motion incorporated / modeled in the FLAC analysis, for example? Were measured ground motions input to the model, or similar to a pseudostatic analysis, did you use some kind of seismic coefficient? Where do I find the podcast? I hope you found the podcast right here. So to answer the ground motion question, great question. What Jala did is there were a number of rock recording sites, and I think that's on slide number, let me give you the slide number. So there were rock recording sites, and Jala took the rock recordings and scaled it to the ground motion, peak horizontal ground acceleration that we thought developed at the site. So if the rock motion was closer to the epicenter, we scaled the record down. If it was farther away, he scaled the record up. So on slide number 35 of the presentation is a list of the rock sites. And then slide number 36 is the attenuation relationship that shows the decrease in peak horizontal ground acceleration from the epicenter to the particular site we were looking at, which happened to be about 380 kilometers away. So you can go into the attenuation relationship at any distance, pick up the peak horizontal ground acceleration that might be applicable to your site, and then scale the ground motion, the recorded ground motions up or down, and then apply that stress time history or ground motion time history to the bottom of your FLAC model. Great question. Okay, number 2. Excellent presentation. Would landfill plastics, organic decomposition, and perched liquid of landfills complicate these analyses? Yes, they surely would. Certainly the liquids perched in the landfill could complicate it because the waste will behave differently, certainly under the seismic loading part. Organic decomposition, Jala was already considering because the modified CAM clay model, he ran it for a 10-year period, and that added additional shear displacements on the critical interface. As far as plastics go, we did not modify the material properties we use for municipal solid waste for additional plastics or not. We based those properties on back analyses of some slope failures as well as laboratory testing of MSW. Okay, number 3. Any predicted differences between calendared and blown film type geomembranes? Absolutely. So in general, calendared geomembranes generally have a smoother surface, top and bottom of the geomembrane, than a blown film textured geomembrane. However, the blown film texture geomembrane must specify a suitable asperity height to get a high interface strength. There are some typical or commonly used specifications for blown film geomembranes that only specify an asperity height of 10 mil. So it's a not very aggressive texturing, and it almost ends up to be close to a calendared geomembrane. So if you are designing and specifying a blown film type geomembrane, make sure you specify a high asperity height. And you can figure out how high it should be by running direct shear tests on geomembranes with different asperity heights and seeing which asperity height generates a strength envelope that gives you the desired factor of safety, for example, 1.5. And then all of your specifications for the geomembrane should say an asperity height that yields a interface strength envelope that exceeds the one presented that you obtained from direct shear testing that yields a factor of safety greater than 1.5. Okay, so in other words, don't just specify an asperity height. Make sure the asperity height gives you the interface strength envelope that you need to meet your factor of safety, both static and seismic analyses, whether that's permanent deformation or a pseudostatic factor of safety. Okay, last question from the survey after the webinar. Number 4, which interfaces represent failure planes, and were those a function of normal load, for example, subgrade versus GCL, GCL versus geomembrane, geomembrane versus geotextile? Was effort made to keep the failure plane above the geomembrane? In this particular case, this hypothetical landfill case, we set the interface, the critical interface, to be the top of the secondary geomembrane and the bottom of the leak detection zone that was overlying it. That was observed in a slope failure, so we kept the critical interface there. But you could change the interface to say GCL, geomembrane, or geomembrane geotextile in the analysis if you wanted to. If your direct shear or ring shear testing showed the critical interface was not the secondary geomembrane, secondary geosynthetic drainage composite, you could change it and put different stiffness and interface strength values in for that interface you want to consider. The stiffness of the interface is a function of the normal stress being applied to the interface, and that's an important feature that Jala added to the model. No effort was made to keep the failure plane above the geomembrane. Okay, so if you have additional questions, please email me or Jala. Thank you so much for all of these excellent questions and attending the webinar. Thanks to Jala for joining me again from China. And Jala, do you want to say anything before we end?
No, it's good. Welcome for questions.
Great, and email Jala for the paper and the fish code. So if you have any other questions, also email Jala, me, or fabricatedgeomembrane@gmail.com. You can download the webinar slides from the FGI website at fabricatedgeomembrane.com. And thank you so much for attending the webinar and listening to the podcast. We hope to see you again on another webinar and podcast. Thanks.